Alright, let's talk more about linear combinations. Last time we looked at what a linear combination of vectors is. So do you remember, if you have k vectors, v1 through vk, what's a linear combination of those vectors? In other words, what's the definition of a linear combination? It's a vector, say w, that what? What makes it a linear combination? It's of the form c1 v1 plus c2 v2 plus dot 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 plus ck vk. Right, that's the definition of a linear combination of the vectors v1 through vk. And we saw how to translate this question, how to tell whether a vector is a linear combination of some other vectors, by rewriting it as a system of linear equations and then seeing whether or not that system has a solution or not. So let's look at another example. But before we do that, we're going to introduce a vocab term called the span. So let's look at a definition. So if v1 through vk are vectors in Rn, the span of these vectors technically it should be the span of the set of vectors. The span of this set is the set of all linear combinations of v1 through vk. So in other words, if you have a bunch of vectors, v1 through vk, then you take all the linear combinations, right? That collection of linear combinations, that's the span. Okay. So let's look at an example. First of all, notice that v1 is in the span of, is an element in, let's use the notation span of v1 through vk. Because, how do we know that v1 is an element of the span of v1 through vk? Well, again, let's pause and ask ourselves what that is even asking, right? What is that even saying? It's saying that v1 is a linear combination of v1 through vk, which means that you can come up with scalars c1 through ck such that c1 v1 plus dot 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 plus ck vk is v1. And which scalars will work? You can take c1 to be 1, and then c2 to be 0, c3 to be 0, all the way to ck equals 0. Right? If you do c1 is 0, c1 is 1, then you get 1 v1 is v1, and then all the other vectors are going to be 0, so then you just get v1. So that shows that v1 is in the span of v1 through vk, and so similarly, what about the other vectors? Vi, every, V1, V2, V3, etc., all those are in the span of V1 through Vk. Vi is in the span of V1 through Vk because because Vi is just 1 times Vi, right? Plus, 0 times everything else. So how can I write this? One way to write it, maybe to make it clearer, would be to say, I can't erase. Like 0 V1 plus 0 V2 plus dot dot dot, and then plus 1 V1, 1 Vi plus dot dot plus 0 Vk. In other words, you're just making all the constants 0 except for the ith constant, which you're making equal to 1. Okay. This might be kind of unclear because, if V1, if I is 1, then I'm taking the constant to be 1, right? And basically I'm taking the ith constant to be 1, and then all the other constants are 0. So it might be even clearer to say something like, maybe instead of doing this, it might be more accurate to say this is equal to C1 V1 plus dot 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 plus Ci Vi plus dot 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 plus Ck Vk, where Ci is 1 and all other scalars are 0. There. Okay. So whenever you have these k vectors and you consider the span, those k vectors are also in the span. Okay. What about the 0 vector? Is the 0 vector an element of the span of V1 through Vk? Well, what do you think? Well, the answer is yes. Because how do we justify that it is in the span? You have to write the 0 vector as a linear combination of V1 through Vk. And what constants can you use? You can make all the constants equal to 0, because the 0 vector is equal to 0 V1 plus dot 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 plus 0 Vk. So notice that these constants can be any constants, right? They can all be 0. It might be that none of them are 0. It could be that some of them are 0 and some of them are not 0. I mean, they're just any real numbers. So whenever you have a collection of vectors V1 through Vk, the 0 vector is always in the span. Okay. Let's do a couple more examples with actual, specific vectors, and then we'll look at some pictures maybe. So we're just practicing using our vocabulary. Is the vector 1, 0, 0 an element of the span of 2, 1, 1 and 1, 2, 3? Let's say you're asked this question. Well, how can we answer this question? Again, let's think about how to rephrase this question without using the word span. So this is asking, is this vector is this vector a linear combination of these two? That's what it's asking. So i.e., is this vector a linear combination of 2, 1, 1 and 1, 2, 3? And we went over how to do this, right? So you want to take a minute and answer this question? Okay, you might want to pause and answer the question and see what you get. But let's go over the answer. So what I would do is, and you can form the augmented matrix where you have these two as the columns in the coefficient part. So 2, 1, 1, 1, 2, 3, and then 1, 0, 0. And you're trying to see whether so if you don't know why I can do this, go back and watch the video about the linear combinations, because I went over that. Okay, so now we have to row reduce this and see whether the system that corresponds to this augmented matrix has a solution. Okay, well, one thing I can do, since I have a 2 here, is I can swap these two so that I get a 1. So let's do that. 1, 2, 0, 2, 1, 1, 1, 3, 0. And that just makes it easier to row reduce. So now I can remember I have this pivot, this 1, and I need to make all the numbers below it equal to 0. So I'm going to change row 2 to row 2 minus 2 row 1. So if I do that, I'm going to get 0, negative 3, 1. Right? And then I need to knock down this 1 here in the bottom row, and so I can just do row 3 minus row 2. That's easy. 0, 1, 0. Okay. And now I have this. I have a pivot here. I have a pivot here. One thing I can do is I can swap these two rows, so that way I'll get a 1. Oops. And then I have these two pivots, the 1s, and then I can do row 3 plus 3 row 2. So then this is going to give me 0, 0, and then 1. And so what does that tell me? Does the system have a solution, or does it have no solutions? It has no solutions, because you can see this bottom row, I have zeros in the coefficient part, but I have a non-zero number here. So this bottom row just says 0 is equal to 1, which is not possible, obviously, because 0 is not equal to 1. And so the system has no solutions, so the answer is no. Right. So let's just write out. In the previous video, I didn't actually write out all the words. So since this system has no solutions, in some books they call it inconsistent. Since the system is inconsistent, meaning it has no solutions, what do we conclude? 1, 0, 0 is not, you can use is an element of symbol with like a dash through it to say it's not in the span. So it's not in the span of 2, 1, 1 and 1, 2, 3. Perfect. And let's do one more. Let's do show that the span of 2, 1, 1, 1, 2, 3, and 1, 0, 0 is equal to R3. All right. Well, what would we do here? We have these three vectors in R3. Let's make it more visible. You have these three vectors, still not very visible. You have these three vectors in R3, right? And whenever you have a bunch of vectors, they're going to have a span. Now that span might be, well, these vectors are in R3. The span might be R3, but it might not be R3. And in this question, we're asked to show that it is R3. Well, what that means, right, what we're trying to show is that every vector in R3 is a linear combination of these three vectors. So let's just write that down. So i.e., we need to show that every vector in R3, let's call these vectors v1, v2, and v3. So we want to show that every vector in R3 is a linear combination of what? Of these three vectors, of v1, v2, and v3. Right. Now, how do we answer that question? Well, let's say that you have a vector a, b, c. Okay, so again, we're thinking about how to translate this into something we can actually do. So let's say that you have a vector a, b, c, right? This is just your generic vector in R3. That this is a linear combination of v1 and v2 and v3 no matter what a, b, and c are. So what you have to do is you have to start off with a generic vector in R3. So this is our generic vector in R3, right? This is like random vector in R3, and show that this vector, you don't know anything about it, it's just a vector in R3, is a linear combination of these three vectors. And if you do that, that shows that every vector in R3, because this is just a generic vector in R3, you don't know anything about it, it's just R3, that is a linear combination of these three vectors, v1, v2, and v3. Okay. So now we have to show that, oops, I need to use the pen, that when you put these vectors v1, v2, and v3 into an augmented matrix and you have a, b, c, that this system has a solution, right? And again, you're not solving, what are we solving for? We're not solving for a, b, and c. We're starting with an a, b, and c. Right? We're given an a, b, and c, but what we're trying to solve for is this whole system. We're trying to see, is this equal to c1 v1 plus c2 v2 plus c3 v3? Is it possible to come up with a c1, a c2, and a c3 that will make the vector ABC equal to this? So we're trying to figure out, is there a C1, a C2, and a C3? Okay. Because the C1, C2, and C3 will be a solution to this system of equations. Alright, so we row reduce. Oops. And so let's swap rows 2 and 1. Then you can do, so we have a pivot here, and then we need the numbers to be 0, so you can do row 2 minus 2 row 1. And then we can do row 3 turns to row 3 minus row 1. Okay, and now we're done with the first column because I have a pivot here and all the numbers below are 0. So what's the next step? The next step is to go to the second column, and you have a pivot here, but I have a 1 below it, so it just makes it easier to well, I guess you don't have, I was going to swap rows 2 and 3, but I guess you don't have to. You could also, because we're really just trying to get the number below to be 0. So you can do that by doing row 3 turns into row 2 plus 3 row 3. Yeah, but the thing is that so I don't really want to do that because generally what I'm trying to push is that when you're trying to manipulate, I mean that works, but generally when we have row reduction, you want to turn row 3 into row 3, you know, minus a multiple of a different row. You usually don't want to multiply row 3 by something. So just to be a bit more consistent, I actually am going to swap rows 2 and 3. And then I'm going to do row 3 turns to row 3 plus 3 row 2. So what am I going to get? Well, I think I'm still going to get a 1 here, and then I'm going to get a minus 2b plus 3 times c minus b. Which you can simplify. But to answer this question, so now that we're here, what can we conclude? This system does have a solution, right? Because I have, when I read these equations, this bottom row, see, I don't have a row of zeros in the augmented, in the coefficient part, I mean. In the coefficient part, right, in this part, I don't have a row of zeros. So what that means is I'm always going to be able to solve the system. Because if you think about it, this bottom row is going to tell me that C3 equals, this bottom row tells me that C3 is equal to this. That's what C3 is equal to. And then the second row is going to tell me, so C3 is going to equal, C3 is going to equal that. And then C2 is going to equal, the second row tells me that C2 is equal to this. So C2 is equal to. And then from the first row, this is C1 plus 2C2 equals B. And then I can solve, once I plug in C2, I can solve for C1. So I do have a solution. I can solve for C1 and C2 and C3 in terms of A, B, and C. So that shows, so the system is consistent. So the span of V1, V2, V3 is equal to R3. Okay, one small thing that I kind of skipped over is technically I showed that if you have something here, that it is an element here. And technically, to show that two sets are equal, I need to show that if I start with something in the span, I get something in R3. But that's just true in general because V1, V2, and V3 are elements of R3. Right? So any linear combination is going to be in R3. Okay. But the main kind of bulk of the problem is to show the reverse, that whenever you have a vector in R3, it is a linear combination of these three vectors, V1, V2, and V3. Okay. So yeah. Okay, that's the answer. We just did the problem. Okay, so, and maybe before we go on, let's just notice this. If you think about it, did we really have to solve the whole system? Well, kind of, but then when you think about it, you didn't actually have to solve for C1 and C2 and C3 all the way. Once you got here, once you got this coefficient part of the matrix, that already told you that those three vectors span R3. Right? Because the only way the system is going to have no solutions is if you have a zero row at the bottom and then something that's not zero in the augmented part, right? But here you don't have any row zeros, so that tells you that these vectors will span R3. Okay. So let's just write that down. So if you have K, so notice that if you have K vectors in Rn, then what you can do is you can make these the columns of this matrix. And if you row reduce, so you compute that echelon form, if the row echelon form has no zero row, so that means that there's a pivot in every row. So you compute the echelon form. If the reduced echelon form has a pivot in every row, i.e. no zero rows. Okay. And again, this is not the augmented part. This is not the augmented matrix. This is the, let's call this matrix A. I'm talking about this matrix, this one, okay? Not the augment, not the whole thing. I'm just talking about this. If this has a pivot in every row, in other words, there's no zero rows, then the span of V1 through Vk is equal to Rn. Because, and why is that? Well, because of what we just did, right? If you have a pivot in every row, so here you have a pivot in every row, then you're always going to be able to solve the system of equations. Right? At the end, there's always going to be a solution. A solution to this equation. You're always going to be able to solve for C1, C2, and C3. And then in this case, you're always going to be able to solve for C1 through CK. Okay. So maybe I'll just end the video now, and then next time we'll take a look at some more pictures, because I didn't really draw any pictures. We just kind of did some sample problems. But next time we'll look at some pictures. Okay.